Okay, welcome everyone. Thank you for joining us for Advances in Multi-Level Signaling from Automotive to Data Centers. Today we have two wonderful Keysight experts, Graham Riley and Luis Boluna. And on the line as well in the chat room, we have Hisu Lee and Cindy Chui, and also Pega Alavi have joined us. So if you have questions, enter them in chat. We'll take them as we can. And Graham, you now have the floor.
Thank you, Carmina. My name is Graham Riley. I'm an application engineer for Keysight's PathWave EDA program. I primarily support the Advanced Design System, ADS, and also System View. And in case you're wondering, I don't normally dress like that for work, but I do sing in a classical chorus. Just wanted to put this up here. So this is the world that we're entering now with multi-level signaling. Or is it? I think perhaps this picture overstates the case that NRZ is going away, and maybe it's something for the past. There's plenty of NRZ type design around, and there will be for the foreseeable future. But certainly there are compelling reasons to want to go to multi-level signaling, and we're going to talk about those in today's presentation. So let's look at the agenda. Okay, so this is what we're going to look at today. I think it's good for us to review how we've gotten where we are today as an industry in terms of the adoption and the driving forces for multi-level signaling. We'll examine some of the design challenges that are out there in terms of working with multi-level signaling. We'll then go into some of the things that you should be doing preparing for design success as multi-level signaling is increasingly adopted. We'll look at some of those standards, and then I'm going to show you three example ADS simulations so that you can see how you actually can use ADS in your work in designing these kinds of multi-level systems. And then I'm going to pass on to Luis. After that, he's going to talk about a little bit about compliance, multi-level signaling, and some of the hardware that goes with it. And then at the end, we'll have a Q&A session. So that's the agenda that we're going to work through. So let's look at the history. What's the goal of a communication system? Getting information from A to B trouble-free. And we're going to do the baseband version today, no antennas, no carrier waves, nothing like that. We're just going to think about real signals. How do we measure that? In real terms, it's error rate. And the biggest channel, of course, is the channel. It challenges the channel. It's really the one thing that we have to work with to make sure that we can, in fact, pass information. So when data rates were low, like with the Morse key I show you there, all that we needed was a piece of copper, really, to get the connection, and Ohm's law in the sense of the losses and so on were just really down to ohmic resistance. Of course, data rates got higher. We started working with transmission line type designs, and we started thinking about it as a true channel. And people were concerned about things like edge rates and reflections. Then, of course, in the last 10 years or more, we started getting into gigabits per second. And now we discovered that the channel is not really just a transmission line, it's a low-pass filter. Lots of high-frequency losses. We started to see things like crosstalk, and noise really did start to become part of the thinking of designing a system. So where are we today, or have we been in the past few years? Well, we got into tens of gigabits per second. And the channel then started to become very difficult to work with in the sense that, you have many different things that now started to come into play and fight that ability to get a good error rate over a link. We have fundamental loss due to the copper and electrics in the system. Geometries started to become sensitive, board repeatability, board yield, system yield, and those kinds of things started to really become very challenging. So how do we deal with that as an industry, as a designer? So we typically have a game plan, and this is what we follow. We do the best we can with the physical design. We make a better channel, so we use better materials, design rules, back drilling, other techniques. We use a lot of EM modeling in order for us to make sure that the channel, the thing that we're sending the data across, is the best it can be. Then we look at signal design. So this is making the signal suitable or conditioning it for the channel that we actually have to address in any given system. And really, there's three essential items to this. I mean, line coding, which is always there. So that's things like NRZ and PAM4, and we're going to talk about that as we go along. Block coding, which is a way of formatting the signal so that you don't have baseline wander and DC content and things of that nature. So 8B, 10B, 4B, 5B, and those kinds of things. And then in some systems, error correction. So we assume that there is going to be at the channel some amount of errors that we're going to have to correct for, so we have to build that into the signal as well. And then last but not least, of course, is this electrical design. That's the drivers and receivers. But we started adding EQ a few years ago, and we called it emphasis. And then it's gotten more advanced. There's CTLEs and DFEs and so on that are now part of our system design in order to get the system to work. And then we've had to deal with losses. So we've put in repeaters in the system, and then interference and so on, and kind of jitter that's crept into the system. We've had to also introduce retimers. But we all know, increase the cost, the complexity goes up, the power consumption, latency, and it can be difficult to design for those kinds of things to make them reliable and so on. So is there a thought here that past a certain data rate times channel loss, a figure of merit, if you like, that we run out of options and that there is some kind of, we can't go any further in terms of the data rate that we're trying to push through a system? So how do we get more throughput? This is where multi-level signaling came in. This is really the line coding, if you like, that we do. So instead of NRZ, we've moved to multi-level signaling such as PAM, PAM3, PAM4, PAM8, PAM16, and so on. And what this means is that we're actually putting more than one bit into a transmitted symbol or a bunch of symbols. So if you look at the two spectrum we have here, you can see that the NRZ, so this is for the same amount of data throughput. The NRZ is going to take up more spectrum compared to PAM4 if you were to look at, for example, the first two lobes of the spectrum, which contain most of the signal information. You'll see that on the PAM4, the first two lobes only take 2 gigahertz bandwidth, but whereas on the NRZ, 4. So it's quite clear that there's an advantage here in terms of sending data in less bandwidth. So that's it. This fixes the problem. We just need to increase the number of possible symbols or levels. However, and I think, again, most of you who have started working with multi-level will realize this, there are some new and more challenging aspects to working with multi-levels that we haven't had to deal with before. One thing, definitely the signal to noise ratio is reduced as the number of levels increases in a signal. What this tends to point to is that the error rates due to noise, which is in the system, will actually be higher typically than for an NRZ system, and we have to keep that in mind when we design. So you'll see that systems now are adopting forward error correction as part of the design, just to deal with that one issue. Eye widths are obviously reduced as well. There are multiple transitions from the, in the case of the PAM4, you can see it here from the lowest to the highest, lowest to the next highest, and so on. And what that tends to do is it makes the crossing area far wider than it would be for NRZ. And the other thing that you'll see is that you'll get asymmetric eye shapes, and you can see that here in this picture. The center eye is quite symmetrical, but the outer two eyes for this PAM4 signal are actually quite differently shaped, and then we have to decide where the decision point and so on is for those eyes as well. So the one thing is clearly that the levels must be linear, so we can be sure that we have the same kind of detectability for each of the eyes, should we say, and that there shouldn't be an offset in time, because if there is, that's going to be you won't be able to optimally sample the eyes. There'll be skew between them. What else is out there that's also new to think about? So equalization, well, DFEs and clock data recovery and so on have got to work for a system that has multiple decision levels. So that's another level of complexity that comes in. And then perhaps one thing that also rears its ugly head when we're working with all of these extra signal processing and focus on linearity is that the power consumption increases for multi-level signaling. So all of those things now become part of the design process, your design considerations when you're working with any given system. So I think I'm going to summarize that by saying we can go faster, we can put more bits through a system for a given bandwidth, but we've also created a number of new and significant challenges. So how do we go beyond that? So how do we make sure that our design work is successful? So I think the first thing is we need comprehensive simulation capability. We need to be able to measure that figure of metric, bit error rate, system error rate, whatever it be. And to that extent, we need to have a capability in simulation world of doing maybe millions of bits per minute in order to get to statistically significant error rate predictions. We can also look at typical eye measures, width and height, bathtubs, contours. We can do mask tests. All of those things can make up that kind of simulation capability that we need. And of course, beyond those system level measures, should we say, we also need to be able to look at different performance of different parts in detail, drivers, receivers, and so on. So we do need to look at waveforms from time to time. We do need to consider the linearity of the transmitter and so on. That's certainly very important. We need to look at timing skew. You can see that here in this diagram here, that there's an offset between the top and bottom eyes compared to the middle one. And we also have to be able to consider jitter. And what is the source of the jitter, what impact is it having, and so on. So being able to diagnose that jitter is also very important too. What else do we need? Models, clearly. The channel itself has to be modeled in detail. I think that's a given. And we need to be thinking about those models in terms of pre-layout, working with good behavioral or line models that really just describe losses and phase length and so on, so we can make sure that our system will work. And then, of course, we take that ideal concept of a certain length of line or connection between two ICs, for example, or connectors through a cable to another connector, and then we have to go into this post-layout world where physical representation becomes part of what we do. So that's all part of the picture that we have here. Those are important. And certainly also transmitters and receivers have to be multi-level capable. And for the most part, the industry is using IBIS AMI to do that modeling at the system level. And I'll show you as we go through this, I'll show you some of the models that we have. And then there's a system-specific model. There's another multi-level system called C-Phy. We'll discuss that briefly. And that actually has its own unique set of requirements. And so if you're working with that, you need a simulation tool that can model that particular system. And then what else do you need? I think clearly a system has to have something that can deal with statistics and swept measurements. Those kinds of things help you as a designer explore the design space to see what control you have, what issues are in there. And you can then also, you can do case studies, you can do standard channel work where you can sweep through different channels and explore the results of a system afterwards. So again, comprehensive simulation capability is certainly one of the most important things that you're going to have to be successful with multi-level. So what else? So the other one, and Lewis is going to spend a good deal of time on this, is compliance testing. So this is really, do I meet the required specification? Can I pass all of those tests for the different test points? And here's an interesting thing. I mean, you will do that anyway for bench measurements and hardware type testing, but you can also do this and should do this with simulated data too. So make sure that when you're simulating a system in sufficient detail, that system simulation also meets the compliance requirements. So how do we make that easy with what we do here at Keysight? We've linked ADS to our scope software. both the Flex DCA and the Infinium. And through that, we have links to our automated test apps, which you can use to set up and test for compliance just as you do on the bench. And it's actually relatively simple to set up, and I will show you that in an example in a few minutes. So that's really looking at compliance. As I said, Luis will give you a lot more detail on that when it's his turn. So I wasn't going to put this in, but I wanted to make a smile. We have you covered on multiple levels, so both for compliance testing and for simulation. So what is out there today? What are people using? Well, certainly PAM-N is the most common form of multi-level signaling that we have. And there are many varieties of this. In fact, I did a Google search on PAM and then a number starting with 3 and going up. And it's surprising that how many of those slots, if you like, are occupied. Someone somewhere has either tried it or is using it. But in terms of the things that are really popular, these are the ones that come out. PAM3 is certainly popular. It's been around quite some time with 100 base T. And more recently, the IEEE has established the 802.3BW and BP, which are specifically related to automotive. And PAM3 tends to be used for those. And recently, it's been discussed that USB 4 version 2 will also be adopting PAM3. On the PAM4 side, well, that's probably more common than any of the others. I think it's been around a while too, 802.3BS, and then 200 gigabit Ethernet, 400 gigabit Ethernet. Certainly PAM4 is in all of those systems today. It's being discussed and I believe will be adopted for PCIe 6. And also it's part of the MIPI standard with A-Phy for the Gear 3 part of A-Phy. PAM5, this isn't broadly common, I think, in design work these days. I mean, maybe some of you are working with it, but it was initially adopted for 1000 base T, and it's still out there and still used for that. So it's in use today. And then PAM8 and PAM16. So we're looking here at MIPI A-Phy again, Gear 4 for PAM8, and then 10G base T, which is a multi-lane solution with some interesting coding schemes, and then the MIPI A-Phy Gear 5, which also uses PAM16. And then last but not least is the MIPI C-Phy, which I wanted to include because it's an important standard. It could well be used in automotive quite a lot. And it's like a 3-wire, 3-phase system. I'm not going to go into great technical description of how it's put together. I'll demo it certainly, but this is an interesting setup because it gets you to 2.28 bits per symbol, which is actually better than PAM4, and it's well suited to the short range, high performance environment for which it's intended, working with 3 wires. So that's just an outline of the kinds of things that we see out there today. It's not an exhaustive list, clearly, but I wanted to be sure that this is you see what kinds of things are out there moving to multi-level signaling. So I'm going to now show you some simulation examples here. So the first one is going to be PAM3. So PAM3 is very well suited to driving twisted pair cables, unshielded twisted pair. And certainly it was used that way for Ethernet with 2, transmit and receive pair. But it's now been adopted by the IEEE with a change that it's actually just using a single pair for the link. And that's something that is certainly quite a challenge to work with in design terms. And what I'm going to show you here and focus on with this is really just to show you how the IBIS AMI models that we have in ADS can work for that system. So let me come out of the presentation and we will go to ADS. So here's ADS. I imagine a number of you have seen ADS and are familiar with it. What I'm going to do is I'm going to put up the schematic for that. So here's a PAM3 schematic design. So what you'll see here is quite simply a transmitter and a receiver with an S parameter representation of a channel. This could be measured data or EM derived data, whatever you would like. And you'll see that this is a channel simulation setup, so it's designed to run many thousands, if not millions of bits. And you'll see that we have two probes here, a receiver in and a receiver out. So let's go ahead and run this simulation. So we're going to run, this is just 10,000 bits. We could certainly run more than this. I'll bring the simulation over. All right. Now what you'll see here is that the receiver is not doing anything at this point in time, but the I at the input to the receiver, and therefore the output of the receiver in this case, is pretty much, well, I should say I's, because there's two I's in this case, are pretty much closed. You can see the waveform here. It's kind of, there's a lot of filtering, if you like, due to that channel that we talked about earlier. So a lot of these high frequency transitions state to state are actually starting to get lost. For example, this one here. So you don't get to see an open eye. So if I run it, if I move this across, and we'll just run this again, but I'm going to change. I'm going to turn on the DFE and the CTLE, and I'll show you how this works in just a second. So I'm going to turn on both the CTLE and the DFE and run the simulation again. The CTLE and DFE are actually contained in the receiver AMI model. So here we go, it's running one more time. And now you can see very clearly how effective that CTLE and DFE have been in cleaning up the signal at the output of the receiver. So these are the kinds of tests that you need to do. You need to understand the signal recovery versus a channel to get from something which is virtually closed to open and clean like this shows a really good receiver design. I have to say in my models are supported inside of ADS. This is a standard format that you'll see for here for PAM3, but PAM4, PAM8, PAM16. There are a number of model-specific parameters, both for the transmitter and also in the receiver. And you'll see here in the receiver that there's CTLE enable, and that was how I was able to turn the CTLE on. And also down here, there's a DFE enable, which is also set to be a variable, and that's how I turned the DFE on. So again, very easy to control as well, and you can go in here and you can start looking at the different parameters of the equalizers and so on. So just in case anyone's going to ask, those models are actually available to you. So if you need that, please contact us. So that's PAM3, a relatively simple setup like that. Let's go back to the slide here again. So now I'm going to look at MIPI C-Phy. Now MIPI C-Phy is an interesting standard. It really is unique as far as I can tell in the industry. It uses a three-wire system called a trio. It has a very interesting and actually somewhat complex, when you look at it, coding methodology. This is a great system, but it does require special testing, special simulations, special models. And the good news is that ADS has those models and is ready to run C-Phy simulations today. You can see that we have essentially three special components that we use. There is the transmitter, the receiver, and the probe, and I'm going to look at those in detail when I run the simulation. And these are the measurements that the probe supports. So you can see there that it does support all of the necessary C-Phy measurements that you would want to do. Also worth noting here, I'll mention it in passing, is that we're working with a triggered eye, which is part of the spec for C-Phy, because the eye diagram is actually the overlay of three different waveforms, which is why you see it the way it is. And noting for those of you who are not familiar with C-Phy, that it's only the center eye that counts. Unlike PAM4, these outer two eyes, if you want to call them that, are not part of the signaling. They exist because of the way the signaling is done. It's that center eye which is the most important thing. So let me come out of that, and we'll go to the C-Phy examples. Sure I have the right ones here. Okay, let's look at this one. So these actually are inside of this same workspace that I think we can make available to you if you need it. So here, this is the setup. Now the interesting thing, we support these models and probes for both our channel simulation and also for the transient engine if you need to do more work at the circuit level. So that's also there. In this case, instead of S parameters, I'm using a multi-layer line library model, a pre-layout, if you like. And here's a definition of the substrate. Here are some of the symbol rates and timings and so on. So we can go ahead and run this. I think I have the data display already open. Make sure I show you the right one. Yeah, it's this one. So when you run this, actually, I've run it twice, once for transient simulation, once for channel. You can see the results are pretty much identical. Here are some waveform plots. The blue is the recovered clock, and the red is the waveform itself. And that clock is used for timing when we're using a triggered eye, like on this one, as opposed to the traditional non-triggered eye here. And that gives us the position of the mask, if you like, for checking whether the system is working or not. So that's really quite simple. I'll quickly go into the setup here. So each of these models, we have a setup here that we can work with. We can talk about symbol rates, the high and the low. All of these things are configurable for you. So, you know, however you want to be setting up your C-Phy transmitter, I think we got you covered. There's even the ability to add equalization at the transmitter side and add jitter at the transmitter side. On the electrical side, we can control the impedances of each of the nodes. And the simulated controls, you know, set to auto, but you have some control there too. So I won't go into that for right now. The receive side is much the same. Now, interestingly, there is a CTLE available inside of here, and if I were to enable that, I can go into this CTLE dialog, if you like, that will allow me to work with the CTLE and the receiver. And you'll see here that I have a bunch of different C-Phy preset equalizations that I can go ahead and select and choose from. So they're in here, along with others, which these are used in standard differential receivers as well. So they appear in the list, but certainly for C-Phy, we have all of these covered here. And if you really wanted to, you could even go in and manually adjust them yourself if that was something that you wanted to try. So that's part of the receiver. Electrical wise, again, we have control over the terminal impedances. So that's a really simple setup, and I showed you the results from that. Oh, I should look at the probe as well. I didn't mention that. So again, this is a setup for the probe. You can see here that we have specific C-Phy parameters related to the mask, and the one thing that's I will point out down here that most important is triggered eye, and that allows us to use that triggered eye setup using the clock to set the way the eye is set up. And the second one here, essentially the reason we have two, one is giving you those triggered results I showed you, and the other one the non-triggered. Okay, let's move on to this one. So the purpose of this one is to show you can include EM post-layout modeling in here as well. So what's happened here, this is nothing too clever. The board section that you see here, part of a foam board, was done and modeled in an EM tool, and we used the layout to create a symbol. So nothing too clever. Essentially, this represents the EM model for the transmission between these three nodes that we have here, and the receiver side where the three nodes are down here. So this is much the same as the pre-layout example, except in this case we're using a model derived from a layout that's been put into perhaps SI Pro, which is one of the EM modeling products that we have. So let me bring up the results for that. So here's the result. Nothing spectacular to see here. It's the same format as before. It's a very short channel on a PCB, so there really isn't an awful lot of degradation. But it does at least allow you to add that to the budget of whatever you're trying to do with that particular C-Phy link. All right, and last but not least, I mentioned in some of the simulation requirements that being able to do sweat measurements and statistics was really important. So here I'm just going to give you a quick sweat measurement example so you can see how that works. What I'm doing here is I'm sweeping the length of this transmission line. So I have a batch simulation controller here. You can have multiple sweat variables if you want. Here I'm going to sweep L, which is the length in centimeters between 2 and 10, and just rerun the simulation. All right, so we need this. This is the result of that. I'm not running the simulations here just to save a little time, but this is the end result. So what I have up here is a parameter sweeper, if you like, through the result data, and I can look and watch what happens as I increase the line length. So here we are at 6 centimeters, 8 centimeters, and then at 10 centimeters, you can clearly visually see here that the mask has been violated. And in fact, if you look down here in the summary table, you'll see that there is a 1 saying, yes, C-Phy mask violated, and it will warn you here. So that's a very quick demonstration of a parameterized simulation using this particular setup. All right, let's move back and go on to the last example here. So now we're going to look at an 802.3 simulation in ADS, and we're going to actually launch the Flex DCA from that. So you can see here, here's a block diagram of a setup for some kind of transceiver. You can see that the various channels are represented here, and in the setup in ADS, they are represented by S parameters. So the chip-to-chip and backplane and so on are right here. So even though they're not labeled, these are can be the various test points that would pop up in the specification. And then what we're going to do is we're going to launch from ADS the Flex DCA, which will open up, and I'll look at the waveform. And then what I'm going to do with this arrow here is I'm going to pass to Luis, and he's going to sort of look at what happens once you've got data into the Flex DCA, how you can then go ahead and run compliance tests for this kind of thing. So let me go back and show you the last demo here. So here I'll just give you a quick tour of this one. So again, we're using a transmitter that's an AMI model, the same on the receiver. And then in between different S parameter files representing the different parts of that overall system. We have some probes in place. I'm not going to be looking at these results, but what I'm going to focus on here is the Flex DCA sync. So if you were to look on the palette here for channel simulation, you'll see that along with the standard probes and the special probe for C-Phy, we have both a Flex DCA and an Infinium link here. I'll just put this on the schematic here, deactivated. They both work in very much the same way. I'll show you what's inside of this one, but it's much the same in concept as for the Infinium. Let me turn that off. So the simulation runs, and after the simulation is run, the Flex DCA will be launched automatically. And how do we do that? So this is the dialog set up for that. So we can do any number of signals, I think up to 8 here, and those would the pin out on the Flex DCA schematic symbol will change accordingly. Chosen dynamic here, that means that instead of just writing to a file and stopping, we'll actually write to a file and launch the Flex DCA, and it will run. This is the configuration of the signal. We're going to make it differential. We're not going to send it to memory. We're going to send it to a slot so we can do some processing on it. And then there's some extra controls down here, which I'm not going to go over today, but certainly now you've seen them, you can go and check those out or come and ask us questions. Connection setup, this is interesting. So how does ADS talk to the Flex DCA? Well, it does through through a network type connection, and that can be local or remote. So if you're able to install the Flex DCA or the Infinium software locally, ADS will run and it will find that installed on your computer and it will launch the window. But if you have it on another computer or piece of equipment, you could also actually run the simulation and send it there. So that's another option for you. So that's how the probe works. I'll go ahead and I'll run it. So I'm just press the simulate key here. You'll see this this will come up as the simulation window, and you notice it's it's messaging the FlexDCA here and starting it up. So in terms of the signals that come in, we really only want to look at the differential signal here. So I'm going to turn off the two single-ended signals so we can just look at the differential signal. And you can see here that this is showing you the PAM levels. And there's a lot of capability in terms of measurements in the FlexDCA, even more than is in ADS, and that's why this is a really useful tool to have. So you have many different kinds of measurements for linearity and under and overshoot and those kinds of things. If you work with the optical side of the business, there's T to Q and other optical type measurements available to you as well. So this is kind of like a diagnostic setup for you. So here you can see I set up a skew measurement, and I can see that there is a little bit of skew between the center eye, which is the reference, and the outer two eyes, as an example of how this signal is set up. In terms of running simulated data, I'll just show you quickly how that works. This is channel 5 that we sent the information to. You'll notice here it says data sim. And if you go into here, you can see that this is pointed to, it's been loaded by ADS, it's been pointed to this file, and then that will go ahead and we're not displaying this right now, but if we let me turn that on, you can see. So that's essentially how we are reading in automatically the simulated data through a file and through this data sim setup. So let me turn that off again. So that's working with the scope locally, but of course, you know, as I was saying earlier, we have this automated test apps, and how do you launch those? Well, let me just show you that, and then I'm going to pass the ball to Luis. Excuse me. If you just look under apps, you'll see here there are I've loaded 3, 802.3, the BS, the CD, and also down here CK. So those are just 3 apps that I actually have installed here.
Well, one of the interesting question came out, especially something around the C-Phy. C-Phy, as Graham talked about, there are 3 eyes, up, middle, and low. But all the measurements are done on the center eye. Like Graham said, it is just waveform shaping. The top and bottom eye are not that important, including all the mask A violations, and the eye width and eye height are all measured on the center eye. So ADS, the C-Phy eye probe are designed to measure all the things based on the center eye. So that's one question came out. And the other interesting question was, something around the PAM tree. When you see that IBIS AMI motor, it is acting as the transmitters and receivers where multiple equalizations, including FFE or DFE or CDR, are involved. And the question is, what about the silicon chips? How do we enter those values, for those type of chips? There are 2 ways. One is, more specifically to C-Phy, the PAM tree, there is a TXR and the kind of parameters where you can just enter the termination impedance there. That is one way. If you like to actually bring the IBIS motor from a specific silicon vendors, that what you could do is to use the different set of the IBIS AMI motor without having those TXR and touch some file, that kind of steps. Then actually you can bring all the silicon behavior based on the extraction on the IBIS motor and make the PAM tree simulations more realistic. But important thing to note here, in order to maintain the most accurate characterization, instead of using just kind of generic, so it is important to use the rear IBIS motor coming from the silicon vendor. I can't tell who is providing those IBIS motor, but that's something, when you start to do rear design, please contact your silicon vendor to get those IBIS motor, then everything will be ready. to start from there. Those were quite important and interesting questions.
Okay, I guess I'll get started then. Thank you everyone for being here and being patient. My name is Luis Boluna, and you just heard from Graham, along with a number of other AEs that I'm sure you know of, such as Pega, Cindy, and myself. We straddle both worlds of measurement and simulation. So we're all basically, we do a lot of validation. So now I straddle more. Some of you may know me. I straddle more on the instrument side of things, but you'll also know me from the past of being in different areas of signal integrity. So let's go into the instrumentation side of things, but I guess I'm saying this is because I want you to understand that of all companies, Keysight straddles both sides. We link the lab to simulation. I know that a lot of you probably don't step foot in the lab, but we are linking tools together, as you can see from what we're going to show you. We've shown you, and we're proceeding in that direction. Okay. So what I'm going to do right now is I'm going to go ahead and take off where Graham left off here. He was showing you a PAM4 simulation, mostly geared towards high-speed Ethernet. So this is an 802.3 CK type of thing. And so I'm going to show you very quickly what my setup is. I'm going to run a simulation. It's a live demo. Many things can happen during a live demo, so bear with me. It should take about 2 minutes once I run the demo, if things go great. And maybe I can keep you entertained for those 2 minutes, and then we'll go ahead and jump into some slides. So in front of you, what you have here is a window. This window is the window of our BERT. BERT is a bit error rate tester, basically a pattern generator connected to an error detector. And I have a separate card on here, which is an AWG, an arbitrary waveform generator. In the past, you've probably seen some DesignCom papers from Heidi where we worked together, and she basically, and I think Hisu was involved in that as well, where we worked together and we basically showed how you can use an AWG to port over simulation results or waveforms into an AWG and use those. So I'd refer you back to that old DesignCom paper, but we use the AWG for many different things here. So in this case, we're just using the pattern generator of the pattern generator of the BERT, and we're sending out a signal. Just like any magician, I don't know if you guys are into the Carbonaro effect. If you are not, I suggest that you go to True TV and watch this guy. He's really good as a magician. But you can see I have a signal on the screen. And just to show you there's nothing up on my sleeve, I will turn this off. And you will notice here there's nothing there. So I am actually dealing with a live signal and turning it back on. There is the signal. We'll put this aside. We're running basically a 53.125 gigabaud signal as expected. We have everything locked on over here. And let's proceed now to do a compliance application test, if you will. I actually already opened this, and you can see here I have some additional results here. So this is what our compliance app looks like. You've seen this already before. And when you first start, you can select what it is that you're looking at. I'm just going to choose something simple, and I'm not going to spend too much time on this, but we'll do like VF, linear fifth pulse response, and maybe signal to noise distortion ratio. Now, as I set this thing off, you'll notice that I have a little window where I can set different options. Of these options, I think one that's extremely important to you guys is this one, run simulated signals. Right now it's set to no. You can set it to yes. If you do set it to, now I accidentally ran this thing on it. If you do set it to yes, what it will do is it'll simply grab whatever's on channel 5A and 5B, and it'll use that. So that's how we port things over from ADS and other type of simulated or saved results, and we can run this in our app. Okay, the GUI that you see here, and sorry, I can't chew gum and do things at the same time here. I have checked my connections. It shows you that these are the connections that you have, and I'm eager to run this because it takes 2 minutes and then I can talk after that. So I'm going to set this up. It is now running. The GUI that you see for this compliance app is pervasive across all of our instrumentation. So you'll see this for PCI Express, USB, MIPI, etc. You'll also see it on our receive testing. Okay, so it's the same look and feel and the same interface. So if you wish to program it with Python, such as I do very often, it has a .NET interface that you can connect to and do many things with. Okay. At the same time, a lot of these apps are being opened up, and we have this simulation, button that or option or configuration, if you will, switch that I just showed you that allows you to go in and send in waveforms. So this guy's running. We can see in the background it's doing its thing. While it's doing its thing, let me review very quickly what I had on the screen a little bit earlier, which is kind of the setup diagram that we have here. So I have basically a BERT, just as I mentioned. The BERT has a remote head. This is the remote head. So think of that as your TX. And then this box that I show here is the oscilloscope. So I'm connected directly to an oscilloscope. This is called a DCA oscilloscope, okay? And I will get into that a little bit later. And in this oscilloscope, obviously, we can embed a channel. We have that option too. I'm not doing that right now. And of course, I'm showing you dotted lines, which could be basically test points. And there's a number of things that we can do inside of here, okay? Let me set this aside again and see where we are. We're still running. And it is now showing you, basically, we're running the linear fit pulse response, which is embedded inside of IEEE. It is basically an algorithm to look at the waveform and try to come up with basically a pulse response. So if you want to think of it, we're doing think of it as a regression of the waveform, if you will. Okay. Let me wait here. And I'm hoping this finishes soon here. We're almost there, and it has completed. Okay. So what we see here as terms of results is we see the different results that we have, lots of beautiful little colors telling you if it passed or failed, different types of margin, and you have a report that comes out that shows you what you've measured. You can click on any one of these different things and it'll take you directly to those portions of the report. Of course, there's a lot more to talk about, a lot more tests to show you. As you can see, let me move this out of the way here. As you can see, there's a ton of other tests. And that's the whole point of the compliance apps. So some of you may have been at the DesignCon papers that we've given in the past, and in one of them, I think that we all participated in. I described what a compliance app is, which is a recipe of Skippy commands. Skippy are basically the commands that go to instrumentation, and so just like Graham showed you earlier, that you have over here on the side, you have a linearity and you have a number of other buttons. That's great, but the combination of steps of using those buttons will lead you to the RLM, the level separation mismatch ratio, okay? Or for example, a combination of additional types of scripts will give you to the linear fit pulse response, ERL, and so forth. So these are basically tests that are done above and beyond, a recipe, if you will, above and beyond what's done inside of ADS, or even done with just simple pushing, simple steps, one button pushes, if you will, on the scope, okay? And I guess I will leave it at that for now and move on. And if I go back to my slides here, so we were talking about multi-level signaling. And multi-level signaling encompasses a number of actual things. As mentioned already, and I won't go into this, you have C-Phy, which is what I'm showing you on the screen here. And C-Phy, I think one of the questions that were asked, and I think was kind of answered by Hisu as well, is that you'll notice this little diamond is off to the side. Clock recovery is done on this edge, and then based on that clock recovery, we sample different thresholds here in the middle of the eye. That's why this looks a little awkward. But in any case, C-Phy, what we're doing is we're looking at different thresholds, and we're subtracting the combination of thresholds at the receiver in order to figure out what type of what we've received, okay? Very similar, we have other things too that fall into this area where we either subtract thresholds or move them around in levels and look at threshold differences, such as dual binary or the application of Hadamard matrices in ENRZ. I think Hadamard matrices is also used in CDMA, but it doesn't fit into this example as well, okay? Now we have PAM, okay? Pulse amplitude modulation. PAM is not new, as was mentioned. I think a while back I did a presentation on forward error correction, and at the time I mentioned, that Voyager, for those Trekkie fans, V'ger, and a number of other things like Marin or whatever, used a lot of forward error correction, and it used a lot of this type of multi-level signaling, if you will, right? And so here what we have is a pulse amplitude modulated signal where we basically encode, we encode what we're looking at, in other words, our binary bits, into a symbol or a level, if you will, okay? This is a constellation diagram. And just as you rotate around the constellation diagram, these are the same boundaries that you see in your eye diagram, and you see the same levels, 0, 1, 2, 3, within a symbol period, okay? Now, I didn't put a slide on this because it was going to get a little bit complicated, but if you had a PAM3, one question that somebody should probably have is, well, wait a minute, how do I fit PAM3 bitwise into those levels? Numbers don't match up, okay? So you're going into a tertiary system when you deal with PAM3. So in other words, one level might represent, or a tertiary system will be 3 bits, right? So those 3 bits represent something. So what we typically have is we have a mapping type of scenario where we take 4 bits into 3 tertiary whatever units. I don't want to call them bits, but hopefully I'm making myself understood. Or 5B6T, or even the famous MLT3, which is not exactly this, but it's something very similar. Okay, there is gray coding involved. You'll notice here that it goes 1110. The reason why we do this in PAM4 specifically is because in the middle, as these eyes degrade, if something happens, we have an error, and we're not sure, we don't know which is the bit that got flipped. We don't know if it's the most significant or the least significant. So by flipping these around, we provide yet another way of trying to mitigate that to some extent, okay? Things to look out for. One thing that you should always do whenever you have an oscilloscope, and I mention this to a lot of people, is a null measurement. A null measurement is basically you disconnect your oscilloscope. Ideally, you would terminate all inputs, but you basically look at a straight line across the screen and look at what is the intrinsic noise of your oscilloscope. I definitely would like you guys to go off and do that, or have your guys do that. You will notice that Keysight is pretty top of the line as far as noise is concerned on most of its oscilloscopes. And you'll notice when you do this, you'll have a histogram that you could look at. And if you look at this, you'll see the VRMS, the voltage RMS of this noise, this null measurement. Now, why is this important? Well, when you deal with something like noise like this and you give it a slope, you'll notice that maps out to an intrinsic jitter, if you will, or phase modulated type of thing, right? So where does that play? Plays into this type of a scenario. So what happens is when you go into PAM3, PAM4, PAM5, etc., you're going to have all these different edges at different slopes, each one contributing different things. What does that mean? Well, what that means is that you're going to basically, depending on where you look at things, and I did this on purpose to exaggerate the example here, is you're going to see multimodal histograms. If you see multimodal histograms, then how do we apply the dual Dirac jitter decomposition? How do we look at things? How do we determine what jitter is? Now things get a little more complicated, okay? So what we do to mitigate this, at least in the IEEE and CEI standards, is we have something called a 12-edge jitter, output jitter model, where basically we designate a number of edges. Now you'll see the first column here, I called everything R0, F0. I called this by the same colors and same names that I had earlier for these edges over here. So each one of these edges maps to that table that I just showed you. I'm going to go back to that table now. And you'll notice that each one of these edges is defined. We define and say, look, these edges will be this transition in our specific PRBS 13Q pattern. So you have to send this pattern, you have to look for these edges, and then you apply your jitter decomposition on those specific edges. Okay, that's what we're doing at these given thresholds. So you can see very quickly, if you have to do jitter by the spec, this becomes kind of basically a programmatic exercise, if you will, if you do this in ADS. Whereas if you do this using our compliance apps, it's all built in, and that's the whole point of our discussion and presentation today. So you'll notice that you can get a number of different things out of the out of the 12-edge jitter model, GRMS, J4U. Think of this as analogous to peak-to-peak jitter, if you will, at 1E-4 error rate. And then EOJ, again, think of this analogous to, well, I'll just leave it at EOJ. Okay, you have linearity. These two are different types of thresholds that we use later in order to figure out some of these other items, such as linear fit pulse response, vertical eye closure. And of course, you can also use the oscilloscope to do equalization optimization. In other words, I can put in FFE at the end of a receiver, and I can use that FFE to basically guess what I should set my TX silicon to, or my BERT de-emphasis to. So you can do things like that. So that gives you a quick overview of why we have these compliance apps and what we do for PAM4. Now, at least I know that in the audience, I did recognize looking and peeking at the audience, some of you are in optics or deal with optics. So we are not specifically covering optics today, but you must understand that PAM also permeates into optics. For example, PAM6 and PAM8 are being looked at for some of the 800 gig stuff. We didn't mention that. So we're not discussing that here, but a lot of this is analogous and applies there as well. So PAM in general. Typically, I walk in, and some of you have seen this slide before. I truly need to update it because you'll notice we have the old colors. And as you well know, these old colors are old, and we definitely want them to have this nice, beautiful black color because that means they're high speed and advanced, right? So this is a slide that I typically show when people say, what do you have for PAM4? And that's an open-ended question. These are all the different type of instruments. But notice that, again, going back to that message I started with, is that I also include system view, ADS, basically PLTS, which has the opens the door to COM, which I think also ADS also has the door into COM. So we're all tied in. Everything's interrelated. If you have a waveform, you can certainly use one of our AWGs. We're actually missing a model here that we're about to release that has 256 gigasamples per second, okay, notably used for optics. And so, you know, there's a number of different instruments that we use to generate signals and look at the error rate of signals. There's the sequential sampling scope, which I'll go into in detail in a minute here, along with different types of sequential sampling scopes, more geared towards the optical community, if you will. And we have real-time scopes. We have a slew of real-time scopes, top of the line, up to 110 gigahertz. And the technology behind this is indeed impressive. Okay. We also use the real-time scopes as error detectors. So as we move higher and higher in speed, look for that. You'll see scopes being used as error detectors as well. So I was asked by my colleagues when we did a quick dry run to maybe go over and talk about Flex DCA and Infinium. We have two different probes in ADS for this, and I'm kind of showing you here is that these are the older models that we have. They've been replaced by newer models that go at clock recovery up to 64 gigabaud. They do PAM4 as well, and you know we have higher speed scopes. Each channel is independent of the other, and you have up to 110 gigahertz bandwidth with these things. Very impressive and huge machines. And you have a line of smaller little scopes, if you will, that are basically the same thing as our DCA without the screen, okay, that also tackle optics. So you'll see here, for example, I have an optical connector here going to an electrical, and you'll have also electrical clock recovery, electrical type of versions of this as well. So I have two different flavors, something called Flex DCA, which is the firmware for our sequential sampling scope, and you have Infinium, which is the firmware for our real-time scopes. Both of them are in Windows 10, okay? So a real-time scope, I think everybody understands hopefully understands what an oscilloscope is. You have a very, very fast oscillator, in this case to do, what we do with this scope, very super fast, high speed, state-of-the-art, type of oscillator, sample very quickly and have deep memory so you can capture as much as you can. That's pretty straightforward. And if you will, actually let me do this as animation. This is a sequential sampling scope, a DCA, if you will. Okay, so what we have here are parts of the scope, and hopefully I'll make you chuckle or smile a little bit. So I'm going to give you an oversimplification, and what I'm showing you here is at least an idea of what happens. In reality, it's slightly different than this, but it's a great way to explain. 4 cameras lined up here, okay? Each camera I can precisely set in time. So I can measure exactly how far each camera is in time, to precisely set the tripods up, have them ready to go. Over here is my trigger. This is my front panel trigger, okay? And I got my finger on it. So at every, 250 kilohertz, I hit this little thing, okay? And when I do that, I take a picture all at once, okay? So now I take a coffee break, go get my second vaccine, whatnot, come back the next day, and I take another picture. The point is I exaggerated between triggers. The triggers take a long time, kilohertz between time. And so by the time I take the next picture, I've moved everything precisely over by a certain amount, which corresponds to a very high sampling rate. So the idea here is you build a very good high-end, wide bandwidth analog front end, but you don't have to worry about running this oscillator at super high speed like you would for a real-time scope. And the result is that you can then very cleanly space out the distance between the dots that you have, and then you can draw something on the screen. Now, this is not exactly reality. It illustrates things. In reality, what we're doing is the first camera is set to a particular time, the second camera is set to a little bit more of a delay, and so forth and so forth, okay? And we take pictures. This is out of one of our data sheets, our application notes, sorry. But this is not also reality, because as you dig a little bit deeper into it, if you don't randomize your sampling across the screen, you're gonna see periodicity issues, right, as well. So it's somewhere in between, but it gives you an idea how you can see how this is not exactly like a real-time scope. It's a little bit different, okay? And a lot of us who are, don't typically deal with having one foot in lab may not know of this, so I'm just bringing that out and letting you know. And that's how we use the scope. Mostly it started with optics, and we use it now for electrical, very high-speed stuff, eye diagrams, and so forth. Over the years, we've added more things such as pattern locks, and other type of things to it. Okay, let's change gears and go to. The idea is we're going to go from data center to automotive, and I am not watching my time, so if I'm eating up time here, please, Carmina or Graham or somebody let me know. Okay.
Yeah, you're doing good so far.
Sounds good. So let's wrap up then with automotive. So on a car nowadays, we're seeing more and more interfaces. And a lot of these interfaces are indeed multi-level, okay? And as you go through and look at these and see what's happening is we're starting to add more things to automotive type of applications, not only from sensor point of view, but also from a computational point of view, such that a lot of us are seeing something that looks like this marketing slide. So in the future, we're going to be actually dealing with these high-speed interfaces in a vehicle. So that's something very interesting. However, as far as the present is concerned with regards to Ethernet, PAM3 specifically, and different types of automotive applications, we have that as well. So as you will notice here, I'm showing you the AE6910T. You'll notice that HP and Keysight are very fond of these great acronyms. So this part number talks about the automotive Ethernet application, where you can run the IEEE 100, 10100 or 1000 base Ethernet, okay, if you will. And the 1000 base is based on PAM3. Okay, same look and feel. I'm going to try to, I have a little packaged up sort of demo that I will show you in a minute here. But you can see same look and feel. Again, you have a setup, select test, configure, run, and so forth. Number of different tests that can be done with this app. And you can see here, I'm showing you just a few of them. And again, they cover the spec. Now, again, the beauty of having compliance apps is that we update them. So as soon as the standard changes something, we go ahead and change that for you, and it's already, wrapped up as a separate test or as a modification to one of these tests. Case in point is what I showed you earlier, the 802.3CK app from IEEE is now in draft 2.0, and we are now reviewing a lot of feedback with regards to that. But we modify our apps, and we are bringing our app up to draft 2.0, and we will have that ready for you soon, perhaps in the summer time. But we keep changing things as we go and keep things updated. I think you already saw this. I'll try to skip through this, but the output of the app will give you a nice little table, if you will, and it'll give you test reports. In my case, I go a step further. I actually extract the data and I put it into spreadsheets, if you will. So there is a way to pull out all of this data, put it into databases, SQL, spreadsheet, whatever. We also, with our oscilloscopes, we offer a lot of protocol debugging. So you may have noticed that we mentioned that you can bring a waveform over to a scope as a memory. So if you bring it over as a memory waveform, you can bring it in as channel 5A, as you will, or a memory waveform. You can then go ahead and apply protocol decoding on it. So this might be very useful in many cases. Here's an example we're showing automotive. We cover a wide range of protocols. Wide meaning anything from a generic type of I2C to MIPI to PCI Express, USB to automotive, and including Ethernet, okay, and memory. That's all I had right now. So let me then switch over and give you a quick little demo then, and then pass things back. this oscilloscope that I have on the screen right now, this is an MXR. It is, we have a number of oscilloscopes. We have the S series, the MXR, which is, this is a particular one, is an 8-channel oscilloscope. And we have basically the UXR, which covers anywhere from a very, I don't know what the lowest is. I think it takes over after S series. So let's say somewhere after 8 gigahertz, all the way up to 110 gigahertz, okay? And so what you see here is a packaged up, everything that I'm showing you here is packaged up. It's not actually live, okay? I don't have anything set up in the lab right now to show you, but this is a packaged up PAM3 that I have here. And you can see in PAM3, I basically have the eye height, and you can see if I show you here under setup, and again, the look and feel of this scope is different. This is an infinium scope. This is a real-time scope, okay? And if I show you here, if I went to basically signal type there, sorry, I had a little lapse here. You'll see under signal type, I brought in a memory, something I've already saved that I was mentioning I could put in memory. And I set this up as to be PAM3. So you can see I can have C-Phy, PAM3, PAM4, different types of multi-level signaling, okay, already built in. So in this particular case, PAM3, you can utilize the wizard to set everything up. Clock recovery is done in software, not in hardware, and that allows us to do a number of different things, okay? And so, great, that's great. If we went under, if we went under launch applications, we have a few applications here. We have a slew of different types of applications. So we don't have the time in this particular webinar to describe everything, but we can go to town here. There's a number of things, but we're going to concentrate again on the automotive. So I happen to have already opened this up here. It's sitting here on the side. This is the automotive app. The automotive app, I loaded in something I've run previously, and you can see here I could set up to Ethernet or Open Alliance, and I can set up, cancel that. And I can set up a number of different speeds or data rates, if you will, okay? Cancel that as well. And again, you can select different tests. Once you've already run a test, you'll see little green arrows or red X's telling you whether something passed or failed, okay? The pass or fail criteria is handled by a particular file that we have in these compliance apps. It's known as a limit file. Do not modify the file, at least not without making a copy. You're going to be sorry, but at least you can look at those type of files and understand what the limits are, what we're dealing with. Nonetheless, once you've actually run the app and you see a report, you'll notice that we have these type of things where we say warning or what's critical, and we have this margin, right? So you can see the actual value, the past limits of each thing, and how much margin you have. And if you need to flag something, you can always flag it. Within the app, what we didn't show you is if you went to preferences, okay, from view to preferences, and under preferences, I believe you go to where it says results. Thank goodness I clicked on the right one. And under results, you'll see margin reporting. You can change the warning to be a different percent, if you will, okay, and you can customize this. Just remember what you did, because the next person that comes by and uses this will probably not appreciate that you move things around for them. But there are customization and different things that we can do here. So, and again, you can see the different tests that we've done, and you can see the different results, including screenshots that are sent and so forth. And I can also show you the same thing by looking at the result tabs. And if you were to click on any one of these, you can see the screenshot here along with some additional information for each one of these different tests that have been done, okay? The other thing too that I did not mention, since we're dealing with compliance apps and we're spending a lot of time on this, is that the compliance app itself, there's a lot of times that you might want to say, well, what section of the spec is this? What's the reference? What's happening, right? If you click on any one of these tests, for example, this guy, you'll notice there's a window that I hit a little bit before. So if I can get just right on here and lift it up, it tells you about this particular test. It says this is the transmitter test, and it says it comes from IEEE 802.3 BW 2015, and it'll say you the reference. Here's the section, here's what's happening. Okay, so we have a lot of that information. In addition, there's always a help menu. The help menu also tells you the test procedure, which is also known as method of implementation, and gives you more information with regards to different tests as well. Okay, so I think I've exhausted this. So let me go back to my slides here. And if we now go to basically thank you for everything, and here are different resources. And with that, I'll pretty much open the microphone to Graham, and I guess we can take any questions or any comments or anything from here.
Hey, Luis, Hisu, just one question. There was a question about the licensing.
Yes.
What if a customer has a scope? Do they need to have a license for offline version of the software, or they can access one mutual a license to access both of them?
Probably best if you send your information about the particular scope that you have. You didn't mention if it's Infinium or FlexDCA. I am inclined to tell you that you probably do have the offline if it's FlexDCA. For the Infinium offline, that's slightly a different thing, and I would rather not answer that and defer that to check.
Okay.
Make sure I could check that.
Yeah.
So I don't say the wrong thing.
Yeah. Thank you.
Sure.
Questions about availability of the AMI models. The PAM-N transmitter and receiver do ship with ADS. So that question came up. The way you get at them is to go into the example explorer and open the PAM4 example that we have, and then inside of the data directory of that example, the IBIS AMI models for PAM-N are available, and you can copy those into your own workspace. So that's one question I did see.
As we go higher and higher in speed, most of these interfaces will have an intrinsic error rate, and I think that was covered by Graham, and that introduces more and more of the need to have forward error correction. I see one question came up now.
Yeah, Graham, this would be for you. What about system view? That was a topic that was briefly referenced.
Yes.
Yeah, system view. So system view is Keysight's system level tool, if you like. It really has two personalities. One is related almost exclusively to the RF world, but it also has a DSP modeling part to it, and it's a great tool. Actually, it has the ability to build IBIS AMI models. So in the context of what we talked about here today, that's probably one thing I would raise. It allows you to build an algorithmic behavior and run simulations on it. And then when you're happy with it, you can compile directly from the system view user interface with the appropriate license, of course, an IBIS AMI model, which you can then use inside of ADS or other simulators. So yeah, that's System View is a really great tool. You can read more about it on our website, but certainly it's there and great for building IBIS AMI. Another question. What about Ptolemy in comparison to System View? So Ptolemy it's a data flow engine in a similar way to the one that is in System View. In fact, you could kind of say that Ptolemy is a precursor to what System View is today, and Ptolemy is in ADS. So a lot of the data flow technology that is in System View was originally taken from Ptolemy and updated and so on. So yeah, Ptolemy is a data flow engine inside of ADS. System View is its own user interface and really much more strongly focused at the system level designer. For example, all of the customizations, controls, modeling, custom modeling, you can write that all in what we call the MATLAB language. So, much more language based. Ptolemy didn't really have that. So,
well, one last comment before we wrap this training up. We just talked about the multi-level, which is PAM3, PAM, 8, PAM 16, even C-Phy. These are all related SerDes applications, serial link, which has the embedded clocking. But I just wanted to mention this interesting multi-level also expanding to memory applications like a GDDR6X and GDDR7, even possibly DDR6 applications. They are coming with a PAM4, which is very, very interesting. So it's not only a SerDes applications, but also it is expanding to single-landed applications. So the multi-level will be everywhere, including USB for V2. That's the last comment.
Thanks everyone for joining us, and have a wonderful day.